So in this particular question, we have a complex number z given by a plus ib, and an equation that's given is the absolute value of z minus 1 minus I plus 4 divided by 3 times the absolute value of z minus 1 minus I minus 2 equals to 1. So using this condition, we have to show that a squared plus b squared minus 2a minus 2b minus of 7 is equals to 0. So let us begin by considering the given equation. So we have z minus 1 minus I plus 4 divided by 3 times z minus 1 minus I minus 2 equals to 1. So we'll cross multiply, so that leaves us with z minus 1 minus I plus 4 equals to 3 times the absolute value of z minus 1 minus I minus 2. Now we rearrange it, so we have 3 times z minus 1 minus I minus of z minus 1 minus I equals to 4 plus 2. So that leaves us with 2 times the absolute value of z minus 1 minus of I is equals to 6. Now we divide both sides by 2. So we have the absolute value of z minus 1 minus I is equals to 3. Now let us substitute the value of z equals to a plus ib into our equation, and that should give us the absolute value of a plus ib minus of 1 minus of I is equals to 3. Then we arrange the real parts and imaginary part. So we'll have a plus ib minus 1 minus I. So we have a minus 1 as the real part plus I times b minus 1 as the imaginary part. Then we apply the modulus, then we obtain the modulus for the given absolute value. So that would be simply square root of a minus 1 whole square plus b minus 1 whole square is equals to 3. Now we expand it, so that should give us a squared minus 2a plus 1 plus b squared minus 2b plus 1 is equals to 3. Then we have taking the square root on both sides, so we'll have a squared plus b squared minus of 2a minus of 2b plus 2 is equals to the square of 3 will be 9, and finally we'll have a squared plus b squared minus 2a minus 2b plus 2 minus 9, which gives us a negative 7 equals to 0. Let's move on to the next question. So in this question, we have a complex number z given by a plus ib, and an equation is given that the absolute value of 2z plus 1 is equals to the absolute value of z minus 2i. Now we have to show this given equation is true. So let us begin by considering the given equation. So we have absolute value of 2z plus 1 is equals to absolute value of z minus 2i, and we substitute the value of z, which will be absolute value of 2 times a plus ib plus 1 is equals to the absolute value of a plus ib minus 2 of I in the right hand side. Then we have 2a plus 1 as the real part plus I times 2b as the imaginary part, which is equals to a plus I times b minus 2. Then we apply the definition of modulus, which should give us a square root of 2a plus 1 whole squared plus twice of b squared to be equals to the square root of a squared plus b minus 2 whole squared. Now we square both sides, that will get rid of the square root. So we'll have 2a plus 1 squared plus 2b squared equals to a squared plus b minus 2 whole squared. Then we expand 2a plus 1 whole squared using the identity a plus b whole square. So that should give us 4a squared plus 2 times 2a, which is 4a, plus 1 plus 2b squared. That is equals to a squared plus b squared minus 4 times b plus 4. Then we rearrange it. We come by combining all the like terms. So we have 4a squared minus a squared plus 2b squared so I made a small mistake here. So the mistake is 2b squared is 4b squared. So this is 4b squared. So this should be 4b squared minus b squared plus 4a plus 4b equals to 4 minus 1. So that gives us thrice of a squared plus thrice of b squared plus 4a plus 4b equals to 3. Then from the first two terms we factor out 3, leaving us with a squared plus b squared, and from the third and the fourth term we factor out 4, which leaves us with a plus b, and the value is equals to 3, and this proves the given equation. So let's move on to the next question. In this question we have the absolute value of z1 is equals to the absolute value of z2, and it goes on to the nth value of z, and all of those values are equals to 1. So we have to show that the sum of the complex number z1 through zn, and we take the absolute value, that must be equals to the absolute value of the sum of the reciprocals. So let us do that. So we begin by considering the given condition that z of 1, absolute value of z of 1 is equals to the absolute value of z of 2 all the way to the absolute value of z of n, and this value is equals to 1. Now if we square, then this should give us absolute value of z1 squared is equals to absolute value of z2 squared all the way up to the absolute value of zn squared, and still the value is going to be 1 because 1 of squared is equals to 1. Now we know that z1 squared can be rewritten as absolute value of z1 multiplied z1 multiplied to the conjugate of z1, which is equals to z2 multiplied to its conjugate. And we continue, and for the nth term we have zn multiplied to the conjugate, which is also equals to 2. Now we consider the first part. So we have z1 multiplied to its conjugate is equals to 1, so that gives us z1 is equals to 1 over z1 conjugate. Similarly we get for z2, which is equals to the reciprocal of its conjugate, and zn will be equals to its conjugate, the reciprocal of its conjugate. So let us now begin with the left hand side of our proof. So on the left hand side we have the absolute value of the sum of the complex numbers, which we are going to replace by the corresponding values, which is 1 over conjugate of z1 plus 1 over the conjugate of z2 all the way up to 1 over the conjugate of zn. Now we can separate the conjugate and simply write it as the overall conjugate of 1 over z1 plus 1 over z2 plus all the way up to 1 over z of n. Now we know that the absolute value of a given complex number is always equals to the absolute value of its conjugate. So this becomes 1 over z1 plus 1 over z2 plus all the way up to 1 over z of n. So that proves, which is equals to right hand side. So let me state it here. We have applied since absolute value of z is equals to the absolute value of its conjugate. So this is how we prove. So let us move on to the next question. So in this particular question we are given is the complex number 1 plus I multiplied to 1 plus 2I multiplied to 1 plus 3I all the way up to 1 plus m times I is equals to a plus ib. And using this given condition, we have to show that the 2 times 5 times 10 all the way up to 1 plus m squared is equals to a squared plus b squared. So what we do, we take the absolute value on both sides of the given equation. So that would be simply equals to 1 plus I, absolute value of 1 plus I, multiplied to the absolute value of 1 plus 2I multiplied to the absolute value of 1 plus 3I all the way up to the absolute value of 1 plus m times I, which is equals to the absolute value of a plus ib. So with the property that we have used is that absolute value of z1 times z2 to z of n is equals to absolute value of z1 multiplied to absolute value of z2 all the way up to absolute value of z of n. Now we find out the absolute value of 1 plus I, which will be square root of 1 squared plus 1 squared times the absolute value of 1 plus 2I will be 1 squared plus 2 squared times absolute value of 1 plus 3I will be 1 squared plus 3 squared. And we go on, and the last item will be 1 squared plus m squared, which is equals to the square root of a squared plus b squared. So the first value will be the square root of 2 times 1 squared plus 2 squared will be 5 times 1 squared plus 3 squared will be 10 all the way up to 1 squared, which is 1 plus m squared, and this value will be equals to a squared plus b squared, and we finally square both sides, so that leaves us with 2 multiplied to 5 multiplied to 10 all the way up to 1 plus m squared, which is equals to a squared plus b squared. So this is proved. Let's move on to the next question. So in this particular question, we have a complex number z and the equation that the absolute value of z minus 5y over absolute value of z plus 5y is equals to 1. Then we have to check the nature of z. So that means we have to check whether the given complex number z is a purely imaginary number or purely real number, or it's just a simple complex number. So let us begin with the assumption that z, being a complex number, let its value be given by a plus I times b. Now we're going to substitute this value into a given equation, but before that let us cross multiply it. So we have absolute value of z minus 5i is equals to the absolute value of z plus 5i. Now we substitute the value of z, so that would give us a plus ib minus of 5 is equals to a plus ib plus 5 of I. So here I missed the I here. So we have a plus I multiplied by b minus 5 equals to a plus I multiplied by b plus 5. So we applied the definition of a modulus, so that should give us the square root of a squared plus b minus 5 whole squared, which is equals to the square root of a squared plus b plus 5 whole squared. Now squaring both sides, we have a squared plus b minus 5 whole squared is equals to a squared plus b plus 5 whole squared. Now we can cancel out a squared from both the left hand side and the right hand side, and we expand the value of b minus 5 whole squared on the left hand side. That gives us b squared minus 10b plus 25 equals to b squared plus 10b plus 25. So here also we can cancel out b squared from both the sides as well as 25. That leaves us with negative 10b. Negative 10b is equals to 10b. So solving for b, we get 10b plus 10b is equals to 0, which gives us 20 times b is equals to 0. So therefore we can say that b value is equals to 0. So a complex number z given by a plus ib. So here the b value is 0. So we see that the z is a real number. So this is purely a real number. So that is the nature of our complex number z. Let's move on to the next question. So in this question we have two complex numbers z1 and z2, and it's given that the absolute value of z1 minus 2z2 over 2 minus z1 times the conjugate of z2 is equals to 1. And it's given that the absolute value of z2 is non-unimodular, so that means its value cannot be equals to 1. We have to prove that the absolute value of z1 is equals to 2. So let us begin by starting with the given equation. So we can rewrite it as absolute value of z1 minus 2z2 divided by the absolute value of 2 minus z1 times the conjugate of z2. So here we are using the property that given to complex numbers z1 and z2. So their absolute value is also equals to dividing their modulus. So we have z1 divided by z2. So let us cross multiply it. So that should give us z1 minus 2 z2 is equals to the absolute value of 2 minus z1 times z2 conjugate. Now what we're going to do in the next step, we are going to square both sides so that the given equation can be rewritten as z1 minus of 2z2 multiplied by z1 bar z1 minus z2 conjugate equals to 2 minus z1 times z2 conjugate multiplied by the conjugate of 2 minus z1 z2 conjugate. So let's do the before multiplication, let's simplify the complex number with the conjugate term. So we have z1 minus of 2 z2. So when we simplify the conjugate, so we'll have z1 conjugate minus the conjugate of 2 will be simply 2, which is a real number, times the conjugate of z2, and this will be equals to 2 minus z1 times z2 conjugate multiplied by the conjugate of 2, which will be simply 2 minus z1 conjugate, and the conjugate of a conjugate is the complex number itself, so we have z2 conjugate of its conjugate will be simply z2. So let us multiply them. So on the left hand side we have z1 multiplied to z1. Let's write it down. We'll reduce it in the next step. So z1 multiplied to its conjugate minus 2 times z1 multiplied to z2 conjugate minus of 2 times multiplied to z1 conjugate times z2 plus 4 times z2 times the conjugate of z2, which is equals to 2 times 2 is 4 minus of 2 z1 conjugate times z2. Then we have minus of 2 z1 multiplied to z2 conjugate and plus z1 times z1 conjugate times z2 times z2 conjugate. Now we know that a complex number multiplied to its conjugate is the absolute value of the complex number squared. So that's here. So we have, now we can also see that we can factor out negative 2z1 times z2 conjugate from both the left hand side and the right hand side. Similarly for 2 times z1 conjugate times z2 can be subtracted from, can be cancelled out from both the left hand side and right hand side, and this leaves us with 4 times z2 times its conjugate will be simply the absolute value of z2 squared, which is equals to 4 plus absolute value of z1 squared times absolute value of z2 squared. Now we bring all the terms to the left hand side. So we have z1 squared minus z1 squared times z2 squared, negative 4 minus 4 times z2 squared, which is equals to 0. Now we can factor out z1 squared, absolute value of z1 squared, from the first term and the second term. So we have absolute value of z1 squared multiplied to 1 minus the absolute value of z2 squared. Then we take a negative 4 common from both sides, so we have negative 4 multiplied by, no, this is plus, so we have 1 minus of the absolute value of z2 squared equals to 0. On further simplification, we have 1 minus absolute value of z2 squared, which we have factored out from the first term and the second term, multiplied by z1 squared minus 4 is equals to 0. So we have 1 minus absolute value of z2 squared is equals to 0, or the absolute value of z1 squared minus of 4 is equals to 0. Now this gives us absolute value of z2 squared is equals to 1, which gives us that the absolute value of z2 is equals to 1. But in the question itself, it's given that this cannot be equals to 1, so we reject this one and we go on to the next solution, which is the absolute value of z1 squared is equals to 4. Taking the square root on both sides gives us the absolute value of z1 to be equals to 2.